Okay, so where are we now? So now let's go to the case that we're actually interested in. We're going to look at the case where f theta is some function g of theta plus another function h of theta, in which g we are going to assume is beta smooth. H for the time being is H we're going to assume is not differentiable at all. Right? Or in the problems that we look at, for example, Lasso, H will not be differentiable, but G will be. So what kind of functions are we talking about? Well, very simply, this G of theta in our Lasso problem is going to be 1 over n norm of phi theta minus y. It's our quadratic loss or empirical risk squared. It's the 2 norm of this. And this is differentiable. It's convex. It's beta smooth. It's very nice. This part here will be our 1 norm of theta. Right? This is not differentiable. So if we have a function of this form, it's a sum of 2 parts, one of which is beta smooth, and the other one of which, for the time being, we say nothing. Then we can develop this not quadratic, but upper bound for g plus h by replacing this with this upper bound, right? So this same upper bound that I wrote down on the previous slide, because this is beta smooth, this function g of theta. Now this one, we're not doing anything with this at the moment. So this is an upper bound. It's not quadratic because this is not necessarily quadratic. But nevertheless, this is an upper bound. So if at each iteration we are finding the minimum of this, we are guaranteed to be moving towards the minimum of this thing here. Okay. So why don't we try that? Why don't we try to minimize this surrogate, this replacement for our function g plus h? This is equivalent to the following. Now, this involves a little bit of algebra, that's all it is. And I'm doing this because we can use a little trick, if you will, based on some algebra. And then we will develop our proximal map solution based on this little trick. So what I'm doing here is I'm changing this problem by replacing this blue thing with this magenta thing here. Why? Well, this is we're minimizing over theta, of course, this function. And I'm saying this is equivalent to minimizing this function instead. So let's expand this. Let's be explicit about what this is. Well, this is beta over 2, this vector dot itself. That's how we get the 2 norm squared. So it's this vector dot itself. Now let's expand this whole thing out. We're going to get theta minus theta I transpose theta minus theta I times beta over 2, which is the 2 norm squared of theta minus theta I. Then we're going to get this transpose this thing here, right? So we're going to get 1 over beta times beta over 2. So we're going to get a half theta minus theta I transpose gradient of g at theta I. And we're going to get the same thing again from this times this, right? Because this is this dot this or this dot this, and they're both the same. It doesn't matter which way around we do the dot product. So that half becomes a 2 because we've got 2 of them. So we get this term here. And then we've got this transpose this. So we've got this gradient dot it with itself times 1 over beta squared times beta over 2. Right? And one of these betas will cancel, and we're going to get 1 over 2 beta times the dot product of this gradient with itself. So that's that term. Now, what are we doing? We're doing a minimization over theta. This depends on theta, so does this, so does this. This doesn't. So we don't need this term, right? Now, so let's get rid of that, and we move to here. So we're minimizing this plus this. Now we can add to this term, which also doesn't depend on theta. And we do not change this minimization over theta because this doesn't depend on theta. We could call it this plus this plus this plus constant, right? Something that doesn't depend on theta. But let's put it in there anyway. Because if we do, we get back to our original problem, which is to minimize this surrogate. So minimizing this surrogate is equivalent to minimizing this instead. And this is the one we are going to work with, because from this, we will see a nice clean explanation of what we actually do in proximal map method. So let's move forwards. So now we can equivalently write for any alpha I, as I said, we can use any step length less than or equal to 1 over beta. This is what we now want to, at each iteration, we want to minimize this. H of theta plus this 1 over, all I've done here is replaced beta, right, with 1 over alpha I. Right, we're going to use some general step length because the step length we were using based on the derivation of gradient descent was 1 over beta. Let's replace that with some general alpha I. So beta becomes 1 over alpha I, or replaced with that. Right. So this is the problem we want to solve. We want to minimize over theta this function. Right. Now let's think about what these two terms are doing. We want to minimize this plus this. So we want to make them both small. So the first term here, what are we trying to do? We're trying to make this as small as possible. And here, we're trying to make this as small as possible, which means keeping theta, our update, as close as possible to the gradient descent update based only on the function g. Right? And this g is a nice beta smooth function. So the first term is trying to get h as small as possible, minimize h, while at the same time keeping theta as close as possible to this gradient descent update based only on minimizing a smooth function, g. Okay, so this motivates now a proximal map. So let me first define what the proximal map is. The proximal map associated to a function, in our case, it would be this function h, which will turn out to be the one norm. And then we will write this update rule in terms of that proximal map. And at that point, this might look a bit circular, but I will explain why we do this. So this proximal map will allow us to do something very special, which is to split the update into two steps or two parts. So first, let me define the proximal map. The proximal map associated to a function. So this is just a general definition so far. The proximal map associated to a function h of theta at a point theta tilde is defined as follows. It's the value of theta that minimizes h of theta plus 1 over 2 alpha 2 norm of theta minus theta tilde squared. So this proximal map, we have this notation for it. Prox alpha h theta tilde. So prox here, h is the function that we associate this proximal map to. So we can have a proximal map for a particular function, and h is the particular function we're interested in here. And eventually this will be our one norm, and it contains a parameter alpha, which is this alpha here. So we indicate the value of that alpha here in the notation for the proximal map. Prox alpha comma h. H is the function, alpha is the parameter. And it's evaluated at some value theta tilde. Right? And that value theta tilde is the theta tilde in here. So this is the general definition of a proximal map. Okay, how does this relate to the problem we've been looking at? Well, it relates as follows. Our update based on our quadratic surrogate or upper bound is the proximal map with the function h associated to the function h with parameter alpha I evaluated at theta tilde is theta I minus alpha I gradient of g at theta I, which is what? It's the gradient descent update based on the smooth function, beta smooth function g. That's what this is. So our update is just the proximal map, the way we have defined it, with parameter alpha I associated to the function h. Right? This is what it was. So what is this? From the definition I've given of the proximal map associated to a function h with some parameter alpha, this is precisely prox alpha I, because we're using the value alpha I here. Sorry, it's here. Because we defined it as h of theta plus 1 over 2 alpha norm of theta minus theta tilde squared, and it's the 2 norm. It's the 2 norm here as well. So that's how we're defining prox of alpha h. So if we compare this to this, this is prox, it's argmin of this. Let me put this out here. Prox equals argmin of this over theta. So if we compare this general definition to this, this is prox alpha I, because we're using alpha I for alpha, h, our function h, evaluated at theta tilde is what? So this is prox at theta tilde, right? What's our theta tilde? It's this thing here. Theta minus theta tilde all squared. So it's theta I minus alpha I gradient of g at theta I, right? So this is what our update rule is going to be. And we are guaranteed to be decreasing our function f equals g plus h if we apply this iteratively, right? So going from theta I to theta I plus 1, which I'm calling theta update, and then applying it again, and we keep applying it. Right, that's all well and good, but what the heck is prox, right? But let me first explain what this algorithm is doing, because this can be a little bit confusing at first. It's saying the following. We first perform this gradient update, right? So let me call this gradient update theta naught. We go from theta I to theta I minus this. So this is a gradient descent update based on the smooth function g. And let's say that we apply this gradient descent update, and let's call it theta naught. Then what we do is we perform a proximal step. We pass this theta naught through our proximal map. And we get our theta update, or theta I plus 1. Theta update equals theta I plus 1, which is just the proximal map with parameter alpha I, our function h, evaluated at theta naught, this thing here, which is this by definition. It's the argmin of this function over theta. So this is the two-step procedure that I was talking about. So the second step here involves a minimization of h modified by adding this term to it. So it's like a penalized minimization of h. This part is easy. This part is where all the work will be done. Now, here's the key point, because this is all looking a bit circular. We've gone from defining a problem, this problem here, where this is not going to be differentiable, so we can't find its gradient. So how do we solve this? To essentially just defining this and then rewriting the problem as this. Do this, and then solve this. But on the face of it, it doesn't like we've got very far. We haven't achieved much because we still don't know how to solve this because this is not differentiable. The key point here is that this proximal map, which is the solution to this, has a closed form expression for cases that we will be interested in, corresponding to Lasso And also then we will do the same thing for elastic net and group lasso and sparse group lasso and other methods. We can develop the proximal map, exactly closed form expressions for all these methods. And that's what we're going to do, right? That will be our task going forward. But before we do that, let me mention a couple of special cases. If we set h equals 0, we get back to gradient descent. So let's see why that is. So by definition, theta update now is the proximal map with this alpha I parameter. If we set h equals 0, it's the proximal map for associated to 0, the 0 function, evaluated here. Well, that's by definition the argument of h of theta, which is now 0. So it's just the argument of this, which has a straightforward solution. So this is this thing dotted with itself. So we're going to get 2 times 1 over 2 alpha I. So the 2's cancel. We're going to just get 1 over alpha I theta minus theta I minus alpha I gradient of g at theta I. Close that bracket, and that has to be equal to the 0 vector. Right? So this obviously disappears, and we get theta equals theta I minus this, which is exactly gradient descent. So h equals 0 reduces nicely to gradient descent. Another special case is projected gradient descent, which I'm not going to discuss here. You can see what that means in the optimization videos, and that's for constrained problems anyway. Okay,